Hi everybody and welcome. Today we're going to be taking a look at some more geometric proofs examples, and we're going to be going a little bit into more depth with some things called postulates. So your goal after watching this video will be able to complete geometric proofs and have a better understanding of postulates. So again, not a whole lot that we're adding in today. Still using that same framework as before. We're just going to introduce a few new reasons to that table as our reasoning statements in our proofs. So first, we're going to take a look at some logical statement here that's very commonly used. Maybe we can break this down into a proof and see, is this true? So the slippery slope, it's actually a logical fallacy, so it's not true. So if you ever hear somebody use that slippery slope argument as evidence, know that it's actually not a valid argument. It's not accepted in any form of debate, and actually logical reasoning, it's not a logical reason to take action or not take action. So fun fact, if you didn't know that before, but today using our knowledge and proofs, we're going to kind of double down on this. And again, that same idea that slippery slope doesn't work. So that's our real applied example. So maybe you've seen yourself fall into the slippery slope reasoning before. So you want to go to a party and you start off with a given statement. You have to let me go to the party. And then if you're not allowed to go to the party, maybe you continue with your line of reasoning, your argument here. If I don't go to the party, I'll be a loser and I won't have any friends. So there's your first logical jump. So not going to a party means that we won't have friends. So maybe those things do slightly logically relate. And then here comes a slippery slope. Without friends, you are going to be alone, jobless, and living in a basement. So that's a really big jump. So again, maybe we can see, okay, so party, if we don't go, then we won't have friends. Those can line up. But going from that statement, there are so many things that would need to happen in steps like 3, 4, 5, 6. Oh my gosh, so many things that would need to happen before you get to the age of 30. You are alone, jobless, and living in a basement. So that's why the slippery slope doesn't work, is because, you know, if we think about this quickly, or maybe we're not looking at it carefully, we're like, okay, so maybe they're kind of making a logical jump here. But again, there is nothing logical to link being alone and jobless and in a basement with not going to a party. We lose a few steps in the middle there. That argument is not completed for us here. And we're going to see that with so many slippery slope fallacies, commonly used in politics and things like that. And again, just know if those things come up, that it's actually not a good reason. It doesn't work. There is no real logic behind those statements. It's more maybe just a fear or a scare tactic more than anything else. So nothing to be afraid of there. But also know if you find yourself using it, come up with a better argument. Maybe there's a better reason that you should be able to go to that party. All right, so definition for today, we are looking at postulates. And a postulate is just a statement that is taken to be true without needing proof. So a bunch of examples like this, but if we're going to say something like, okay, angle 2 is a right angle, we can also say that angle 2 is 90 degrees, right? We don't need to prove that. That's what that means, that is true. So other examples that we might see as we're working through, so for example, this is angle 1 and this is angle 2, and it's a linear pair. We don't need to prove. We know that angle 1 plus angle 2 equals 180 degrees. So things like that, we don't have to individually go through and prove why they're true. It's basically things that are definitions, right? We know they're true. It's a postulate, 100%, no doubt, no uncertainty there at all. So a couple of postulates that we can add to our textbook here actually have to do with those transversals we were working on last unit. So the corresponding angles transversal postulate is that if we have two parallel lines and they are cut by a transversal, then we know that all of the corresponding angle pairs are congruent. So last unit when we were saying, we had a diagram like this. I should draw that a little bit bigger, a little bit more space. If we have a diagram like this, we would know that angle 1 and 5 are congruent as long as we said that, these two lines here are parallel. We don't have to prove anything there, we just knew it, right? Angle 1, angle 5, they're good as long as we know those lines are parallel. So the converse of this postulate, or the flip side of that, is that if we have a pair of corresponding angles that we know are congruent, let's make sure I just got kicked out there. We're back. So if we know that 1 and 5 are congruent, then we can also say, based off of that knowledge, that the lines are parallel. So it actually goes both ways. So again, if the lines are parallel, we can say the angles are the same. If the angles are the same, then we can say that the lines are also parallel. That only works. That's not for, those alternate angles and all those things. That postulate only applies to corresponding angles. So if we think back to where we started, I think it was a few lessons ago when we were talking about, why those lines weren't parallel, why we couldn't prove it, is we needed to have corresponding angles for that to be true. We just didn't have those. All right, so some examples today. We're going to go through these step by step, and we'll take a look here. So two lines intersect at point A, and what we're trying to see is that the vertical angles, so the ones that are across from each other, we're trying to say that those are congruent. So trying to say, this angle here and this angle here, are they the same? Or conversely, is this angle and this angle, are those two the same as well? So vertical angles right on top of each other. All right, so let's start off. DE and CB intersect at A. Again, we're given that two lines intersect at point A. Next, DAC, let's trace this out, and DAB equal 180. That is the definition of a linear pair. So bringing in some past vocab here. And that's why it's good to take careful notes on these vocab terms, because they always come back. They're always here for us. All right, now let's try the next one, DAC and DAB, or no, CAE, sorry, CAE, saying that also equals 180. That's also a linear pair. So that's going to be our reasoning here. That's how we know that those equal 180 degrees. All right, so now we're taking this statement and it's going here, and we're taking this statement and it's going here. So it looks like we have A equals B, B equals C, so A equals C. That looks like, to me, a good example of our transitive property. And then now we're just left with DAB and just with CAE. So it looks like we had to subtract DAC, subtract DAC, and to be just left with CAE and DAB. So it looks like a little bit of algebraic reasoning there. So we called that one the subtraction property. And we're just left with the measure of DAB is the measure of CAE. And we're saying that means that they're congruent. So if we remember back to last lesson, that is the definition of congruence. We can use measures and relate it to congruence, and we can use congruence and relate it to measures. So that's an example of a proof for today. So these proofs are getting a little bit more challenging. A couple of extra reasons are coming in here, and we're relying on some old definitions as well to fully go through and process these. But as long as we're going step by step, as long as we're making sure we have a real geometric reason for every one of our steps here, we're going to be in good shape. As always, any questions, let me know. We'll have some more time in class to go through some of these more extended